All right, we are in AP Precalculus doing the notes for topics 1.9 and 1.10. So this is rational functions. I'm guessing topic 1.9 is vertical asymptotes and topic 1.10 is holes. We're covering them both in the same lesson. So again, we're going to go ahead and assume that f of x is the top, g of x is the bottom, and there's some sort of polynomials. I'm going to go ahead and read. You guys are reading along with me. Since we are dividing by polynomial, rational functions must have restrictions on their domain, aka you can't ever divide by zero. We know that we cannot divide by zero, so we must consider any x values where the bottom is set equal to zero and restrict them from the domain. Say, don't accidentally divide by zero. These x values will be the location of either a vertical asymptote or a hole, one or the other. Do you guys know what a hole looks like? A hole looks like this, where you have a graph and a function that comes like this, and then you erase a little bit. You say erase. Oh, I'm going to come back here and change my erasers to a precision eraser. I erase a little bit right here, and I say, you're not allowed to be at that spot. That's called a hole. So you can label this thing, that's a hole. We know what a vertical asymptote from yesterday looks like. It's an electric fence. Instead of being a horizontal line, it's a vertical line. Both of those values are undefined because both of those values have a zero in the denominator. And just reading on, vertical asymptotes and holes both occur when the denominator of the rational function is equal to zero, what I just said. So how can we distinguish between the two when working with these equations? So here's a quick little chart for you to help. A hole occurs when the factor in the denominator cancels out with factors in the numerator. So this is from yesterday's homework assignment, and we can actually talk about that now. So in this case, we have an x minus 1 and an x minus 1 that we can cancel out. Therefore, we have a hole at x is equal to 1. And I'm looking at the vertical asymptotes. Vertical asymptotes occur when a factor in the denominator cannot cancel out with factors in the numerator. So over here, x minus 1, this cannot factor out with, or that cannot cross out with anything in the top. So we have a vertical asymptote at x is equal to 1.
See, they're only now giving us a definition.
I know it's kind of weird, right? Because we had a homework assignment that was talking about that. Yeah. Something that's interesting. For both g of x and these equations, weird things are going on. X minus 1 and x minus 1 are in both of these equations. This one is a hole and this one is a vertical asymptote. Who can tell me why? A vertical asymptote is where you have a leftover in the denominator. What's the difference? Again, I'm going to ignore this 2. I'll actually scribble it out. Ignore the 2. Ignore this x plus 2. What is the difference between the two different g of x's?
I mean, there's 5x minus 1 still.
There's what?
I mean, you see the x minus 1 in parentheses?
I see the x minus 1 in parentheses.
There's like 5 of them.
Well, there's 3 in the top and 2 in the bottom, which means who wins? Which one has a higher degree? So what's left over is the one in the top. This down here will cancel out completely, and the top wins. Over here, who wins? The bottom. Whenever the bottom wins, you'll always have a vertical asymptote. Whenever the top wins, then it's still going to be a hole. If there's a tie, it goes to the hole. So in this case, there's a tie, it goes to the hole. In this case, the bottom wins because there's no even competition in the top. There's no x minus 1 up here. So the bottom wins. When the bottom wins, vertical asymptote. When it's a tie, it's a hole. And I'm going to write that down because I think it's going to be helpful. Whenever you have a tie like x minus 1 over x minus 1, that I consider to be a tie. That will be a hole. Or if you just have, if the top wins, and I'm just going to point down here, if the top wins, then you get a hole. Vertical asymptotes only happens when the bottom wins. When the bottom wins, like here and here, then it will be a vertical asymptote. So far, so good. All right. So in the graph, you can clearly see that we have a hole here at 1, And we do have a vertical asymptote here at -1. And it tells us, yep, there's a hole at 1. We can see that already. And over here, we have a vertical asymptote at x is equal to 1. Nothing too important there. Yep, I don't know what it's saying here. As I approach f of x, or as I approach 1, what's happening? As I get closer and closer to 1, this is the value 1. What do I approach for the height? And this is, I don't know if you guys have seen this limit notation before. If this is raised to the power of a negative sign, this is really saying, and I'll write it in words like you will also write in your notes, this is saying as x goes to 1 from the left. And this one is saying x goes to 1 from the right. That's what these powers of minus sign and power of plus sign really means. And again, this 3 and this 3, these are both heights. So the way that I read this is I say, as I approach 1 from the left, I have a height of 3. As I approach 1 from the right, I approach a height of 3. And that makes sense because these are both approaching 1. So they're both approaching this x value. As I come from the left, I'm approaching this height of 3. As I approach from the right, I'm approaching this height of 3. Both of these are the same height. So far, so good. Whenever I have a hole, usually this is some number, some height, some actual number. But when I have a vertical asymptote, again, as I approach that value of 1 from the left, I will shoot to either positive or negative infinity. These don't have to be opposites. Again, we've seen the volcano before, right? We could have 2 negatives or we could have 2 positives. In this case, I have a negative when I go from the left, and I have a positive when I go from the right. Questions about the limit notation? No questions. All right. We're moving on the backside where we have a bunch of examples. All right. We are trying to find x values for any holes or vertical asymptotes. I have some masks if you want some.
No, that's all right.
Okay,
I'm
there's
just like,
right up there.
I mean, I don't know. I don't think it's a sickness. It's just like a kid, like kids.com.
Okay.
It's like a tickle in my foot.
Okay. All right. So in part A, I'm looking to see if there's any holes or vertical asymptotes. I'm noticing that I have an x plus 3 and an x plus 3. What's going to happen with those x plus 3s? They cancel out. There's a tie. Ties go to vertical asymptotes, zeros, holes, holes. So that means we have a hole at x is equal to what? -3. Good. And look who won in the bottom. X minus 5. What is that called? Is that a hole? Vertical asymptote? Vertical asymptote. You guys can just say VA in my class. I don't want to spell out vertical asymptote. It's too many words. We'll say a VA at x is equal to what? 5. Done. The AP precalculus test, the actual AP, you can also just write VA. They're very used to that notation. Virginia. All right. Notice that the instructions did not ask us to find zeros, but we would have had a 0 at +2, but it didn't ask for that. All right. What's going on with B? Let's look at the x plus 1s first. Who wins? Whenever the bottom wins, that's it's a vertical asymptote. So we're going to have a VA at x is equal to what? -1. Okay, next we have this x minus 2 squared over x minus 2. What happens here? Top wins, therefore hole. Okay, so we're going to have a hole at x is equal to +2. Good. And moving on to part C. This one has not been factored, so let's factor this. This is 1 over what? X times x squared plus 4.
X minus 2x plus 2.
Ooh, careful. When there's a plus sign, there's nothing you can do. And I will make this note like you guys will make it in your notes. This term right here never is equal to 0. Okay, because what we're doing over here is we're setting them equal to 0, which is why the signs are flipping. We can't set that one equal to 0 because it turns imaginary on us. But this one we can set this one equal to 0, and we get x is equal to 0. What is this? Is it a whole? Is it a 0? Is it a VA? What's going on here?
0. 0 is 0.
Good guess, but no. I know it's confusing. Why do we use the word 0? Can't we just use the word x-intercept? Is this an x-intercept? No, it's not. It's a vertical asymptote. Why is it a vertical asymptote? Because this x was the winner of the bottom. Whenever the bottom wins, it's a VA, a vertical asymptote. All right. Now we're doing limits. We're always doing as x approaches 2. So I'll do this. As x approaches 2 for each of the following functions. So here's how we write the limit of our function f of x as x approaches 2. How do I say from the right? To the power of that positive. So 2 from the right. And what is that equal to? So you have to be careful here. Essentially what you're doing is plug in a number slightly bigger than 2, like 2.1 or 2.01 or 2.00001. Those numbers are slightly bigger than 2. So if I plug in 2.1 into this x, 2.1 into this x, and 2.1 into this x, we need to check the sign. All right, this sign will be what? This will be positive. 2.1 minus 1 is 1.1, which is positive. 2.1 plus 3 is positive. And 2.1 minus 2 is positive. So this is a positive on the top, positive on the bottom. Therefore, this entire thing is positive. How do we say it is positive over here? It's going to be positive infinity. Why is it positive infinity? Not as opposed to why it's negative infinity, but like, why isn't it just a number? What type of thing goes to infinity? Is it a... No. Is it a whole? Is it a VA? Is it an x-intercept? What type of thing goes to infinity? It's a VA. VAs always go to positive or negative infinity. So why do we have a vertical asymptote at 2? The bottom has this x minus 2. Therefore, this if I plug in a 2 minus 2, I'll get a 0. Whenever you could have a potential 0 in the denominator, that is always going to be a vertical asymptote after everything has been canceled out. Again, if I was taking the limit as x approach 1 or the limit as x approach negative 3, my answer would be 0. But I'm not asking that. I'm asking what happens when I plug in 2. Okay, let's go ahead and plug in the limit of f of x as x approaches 2 from, oh my goodness.
Yeah, I was about to say that the 2 is negative.
Yeah, you should log it. So this belongs down here. This belongs up here. Today's the 14th. From the right means from the right. This is from the left. So what you're saying is you didn't catch my mistake.
No, what I'm saying is I told you.
What you're saying is you said it right, but you didn't catch my mistake.
No, because I was really looking at the board. I said it right.
You did say it right, but you didn't catch the mistake. Josue did.
At the
It's
end
not,
of
it
this
doesn't
one,
work like that. No, because technically I told you the right answer and then I didn't. I stopped paying attention.
Okay, well, yeah.
There's
Next
a-
time you can get the extra credit once you pay attention.
There's a 31st day of December, right?
Yes.
The 31st, the date's gonna be 1, 2, 3, 1, 2, 3.
I guess if you do it in American.
Yeah, I'm doing it in American.
Okay. All right. What happens when I plug in a number that's left of 2? What is the number that's left of 2? Give me an example.
1.
1 is less than 2, but you have to be careful because 1 actually will make this thing 0. What's a number that's even closer to 2 but left of 2? Try again. 1.9 is really, really close to 2.
Oh, close.
So instead of putting 2.1 in here, what I'm going to do is I'm going to put 1.9, 1.9, 1.9. I'm being like overly thorough by writing this out. You guys should be able to do this in your heads. A number that's really, really close to 2, but left is about 1.9 or 1.99 or 1.99999. That number is really close to 2 without actually being 2. So again, what's 1.9 minus 1? Is it a positive or a negative? Okay, positive. 1.9 plus 3 is a positive. And then here's the change. 1.9 minus 2 is a negative, which is different. Which means the entire thing, as Anatoly said, is negative. How do I say that? Negative infinity. Very good. All right. Moving on to part B. Any questions about part A?
Why didn't I get the
Because you didn't find the mistake.
Yes.
All right. Notice in part B that these two terms will cancel out. What type of value do I have?
Whole.
It's going to be a whole. Everyone label this one. This one is a whole. What type of value did I have in part A? We had a VA, a vertical asymptote. Let's see what happens over here. So again, let's do the limit notation correct this time. The limit of g of x as x approaches 2 from the left, meaning minus sign, and the limit of g of x as x approaches 2 from the right, meaning plus sign. All right.
Oh my goodness.
These numbers will cancel out. The only number that I need to plug into is here and here. When I plug in a number that's really, really close to 2, I should get an actual value out. Because this is a whole, I don't actually need to move over. Over here, I could not plug in 2 because I'm not allowed to plug into something that's undefined. A whole technically is undefined, but I can find its approximate value by just plugging in that number itself. Over here, we plugged in 2.1 and 1.9. Over here, I'm plugging in 2. I'm allowed to just plug it in and see what happens. Because these cancel out. As long as we can't divide by 0, it's okay. Plug in 2 then. So let's plug in 2 to both of these. And what am I going to get? 6 on the top. Negative 1 on the bottom. So this is approaching the height of negative 6. Again, wholes will always approach a height. You'll need a number over here. But a vertical asymptote will always be either a positive or negative infinity.
Did we ever decide when we're going to take our test?
We never have. After this lesson, we should talk about it. And guess what happens when I plug in 2, but on the right side? It's the same value. Because on that front side, we saw that if I have a hole, they don't shoot off to different sides. They always approach the same height. When I approach from the left, I have the same height of 3. When I approach from the right, I have the same height of 3. The height does not change for a hole. It's the same value for the height. So over here, I'm going to come down here and say it's the same height of negative 6. All right. In part C, again, I'm plugging in 2. What do you guys notice about these 2s? What's up? The bottom is bigger. Therefore, what type of feature do we have? It's a VA. This is another VA, which means we're not allowed to actually plug in 2. We need to plug in a number that's really close to 2.
there's no one
Yeah.
in the
That's perfect. All right. So we're going to write out our limit. So it's the limit as x approaches 2 from the left, so minus sign for this h of x function, and the limit as x approaches 2 from the right, meaning plus sign of h of x. Again, we cannot plug in 2 because we have a vertical asymptote, but we can plug in a number really, really close to 2. Saul, what number should we plug in when we're plugging it in on the left?
1.
All right, so each of these values has a 1.9. Each of these values, 1.9. Each of these values, 1.9. Each of these values, 1.9. All right, what are the possible answers? Can I get a number? What am I going to get? Out here, my potential answers, whenever I have a vertical asymptote,
Oh, yeah, you're going to have the positive and negative.
I only care if this answer is positive or negative. This will either shoot to positive infinity or negative infinity. We just need to figure out the sign. So again, ignore the numbers. Over here for a whole, we couldn't ignore the numbers. We wanted the number, but now that's a VA. All we care about is a sign. 1.9 minus 4, positive or negative? Shout out. Shout out. Don't lip read it. Negative. 1.9 minus 2. Negative. 1.9 minus 2 squared.
Positive.
Positive. Anything squared is always a positive. And 1.9 minus 1, positive. So again, negative times negative is a positive. Positive divided by positive is a positive. The answer here is a positive infinity. All right.
You'll get there one day.
Claire, we plugged in 1.9 before. Now what do we plug in? Something bigger than 2. 2.1, 2.1, 2.1, 2.1. Let's see what happens. 2.1 minus 4. Shout out positive or negative? Negative. 2.1 minus 2. Positive. 2.1 minus 2 squared. Always positive. And 2.1 minus 1. Positive. This entire thing is a negative because we have a negative times a positive, so the top is negative. Positive times positive, which is positive. A negative divided by positive is a negative. All right, very good. Moving on to our next example. Example number 3. Write an equation of a rational function with the following limit properties. Ooh, that's interesting. All right, so here's how I interpret this. On the first one, when I get close to the x coordinate of 3, I get the y coordinate 5. 3, 5 needs to be on a graph. When I get close to 1 from the left, 1 from the left, that will shoot down off the graph. The only way to have off the graph is to have a VA. All right. What else do we know? We know that as I approach 3 from the right, I need to have a 5 as well, which means 3, 5 is still on the graph. What probably happened at 3?
Nothing.
It might be nothing. Honestly, it could be nothing.
If it's still on the graph.
But most likely, since we're talking about holes and VAs, if you had to decide between a hole or a VA, what's happening there? It's probably a hole at x is equal to what? At 3, yeah. Which means we have to have our factor needs to have an x minus 3, right? And then as I go to 1 from the right, it's going up off the graph. All right, so what sort of equation should I write here? We need to have a hole. So I have to have an x minus 3 and an x minus 3. Look, now the top and bottom, we can cross them off, and we have a hole at x equals 3. Done. But we need to figure out how to install a vertical asymptote. How am I going to do that? Plug in.
I guess like.
What was the question?
I need to somehow install a vertical asymptote at 1. When I go to 1, I'm at negative infinity. When I go to 1, I'm at positive infinity. How do I make sure that plug in 1 gives me a vertical asymptote?
I don't know.
Well, first of all, vertical asymptote, who wins, top or bottom? The bottom. So what do we need on the bottom?
We need the.
To the power 2.
Well, there needs to be an x in here. And how do I make sure that positive 1 is a 0? This needs to be x
Yeah,
minus 1. That should work. Let's go ahead and just make sure that this works. These essentially cross off, and you can ignore them. When I plug in a number from the left, this will be negative. When I plug in a number from the right, this one will be positive. Everything here works out perfectly. And if you don't believe me, plug in a number like 1.1. 1.1 is a little bit bigger than 1, right? We all nod our heads. 1.1 is a little bit bigger than 1, therefore it's on the right. 1.1 minus 1 is positive, therefore the answer is positive. Seems to check out. If you were to plug in a number that's slightly less than 1, like 0.9, 0.9 is on the left. If I plug in 0.9 here, I get a negative value. And again, I don't have to worry about those x minus 3s. They do cancel out. All right. And that's our function. We can say that's our f of x. F of x is equal to that. All right. There's a problem here. We need, not only does it have a 0 at 3, it needs to have a height of 5. Right now, if I plug in 3, this number will be 3 minus 1, which is 2. If the bottom is 2, what does the top need to be so that the answer here is 5? What divided by 2 is 5? This number needs to be a 10. So let's come back here and put a 10. Now we're good. Because again, it told me, hey, plug in 3, we should get a height of 5. If I plug in 3, those cancel out. 3 minus 1 is 2. 10 divided by 2 is 5. So that actually works out. All right. In part B, again, we have a whole where? A whole at x is equal to
X is equal to.
It's just 4. Isn't that 4 at all?
that's the height. What's the x coordinate?
Oh.
Oh, 2.
Negative 2. Good. We have a vertical asymptote where? Nope.
1.
Negative 1. At negative 1, we have a vertical asymptote. Fourth time's the charm, right? All right, so we're going to have a fraction. This is going to be our f of x. We need to have some sort of whole at x equals negative 2. How do we do that? Top should be... Yeah, but what factor should it be? X what? I want to get out a negative 2. Is it a minus 2 or a plus 2?
No, I said plus 2.
But you said both of them. X plus 2. Okay, you got to... If you get confused, just be like, final answer, I lock in plus 2.
Because I can do math, I can't speak to it. Or whenever you see like some words or something, like the, what's it called, vertical asymptote, I don't know what you're talking about. But then
Oh, okay. Yeah, go for it. All right, we need a vertical asymptote at x equals negative 1. Josue, what does that mean? Vertical asymptote, who wins? Top, bottom, tie? Bottom wins. So down here in the bottom, what are we going to have? Plus 1. It's always the opposite sign. X plus 1. All right, everything is good. We have a vertical asymptote at negative 1. I don't know if the sign is okay. If I plug in slightly less than negative 1, or slightly greater than negative 1 because it's a plus sign, I do get a positive. And just to verify that, a number that's slightly greater than negative 1 is negative 0.9. If I plug in a negative 0.9 into this x right here, these cancel out, so I don't have to worry about that. This x is negative 0.9. This entire number will be positive. That works out. And if I take the reverse of that, it needs to stay positive, which means this, how do we change this so that it stays positive no matter what? Cool little trick. What can I do to this factor to make sure I am always positive no matter what?
Square.
There it is. Square it. Now, no matter what happens, it will always be positive. Last thing, we need to make sure that when I plug in -2, I get out a height of 4. When I plug in -2, those cancel out. Don't worry about them. I have a -2 right here. A -2 plus 1 is a -1. -1 squared is a +1. Right now I have a +1 on the bottom and nothing on the top, and I want this answer to be 4. So the top should be just 4. 4.
Thank you.
What's extra credit? All right. And we have our last example for the notes.
Oh, there's no way we're finishing both interviews, so I listen to it.
We got this. We got this. You might not be able to finish it in class.
That's not just it.
Example 4, sketch a picture of a rational function that has the following properties. For A, it has a hole at x equals 1. What is this saying? Can someone help me interpret that? As x approaches 4 from the left, f of x increases without bound? What does that really mean? What does that mean? As I approach 4, so let's go ahead and say I have a graph at 1, 2, 3, 4. What's happening at this line at x equals 4? As I approach it from the left, as I go from the left, what is my height?
Zero?
How do you say increases without bound?
Yeah, it's constant. Always positive.
Without bound.
What's bound? Infinity.
Infinity is without bound. Yeah.
Positive infinity.
So increases is positive infinity. Without bound, always Anatoly just means infinity. You're boundless. Boundless means you're infinite. So increases without bound is a positive infinity. If you need to write that down in the notes, say increases without bound turns into positive infinity, which means my height goes off the charts. So we'll say the height goes off the charts up here. And when I go from the right, when I come from this direction, I decrease without bound, which means what, Anatoly? What does decrease without bound mean? Decrease without bound means negative infinity, which means I'm going to come out over here and decrease without bound. The only thing that I'm missing is I need to have a hole at x equals 1. So here's 1. I'm going to come over here. I'm going to put a hole and continue the function. So come over here. There's a hole, and then I continue the function.
We just have to draw it?
Just have to draw it. Done.
That's it?
That's it. All right. Last question, and then we're done with the notes. The holes are easy to do because we just erase a little bit. But we want to do our vertical asymptote first. So again, this entire statement was talking about one particular vertical asymptote. Similarly, this will talk about one vertical asymptote. So let's go ahead and make our graph. As I approach -1, so my vertical asymptote is happening here at -1. As I approach it from the left, I decrease without bound. So as I approach it from the left, I decrease without bound. What does that mean, Josue? It goes to negative infinity. So we're going to go and say this goes like this, to negative infinity. We'll come back and erase in a little bit to make sure that we have the correct zeros. And now this is saying as I go to the right of this blue line, this is going to decrease without bound. We already said decrease without bound means negative infinity. So I'm going to have some function that looks like this that comes down. The only thing that we need to do is we need to install these holes at x equals -2 and x is equal to 3. So let's come back here to our eraser. And x equals -2.
Wait, would it be like that? Would it be like this? Or would it be like this? Like an iron going like that? Because if you, that's increasing.
as I go and get closer to this line, getting closer to this line, closer to this line, I shoot off to negative infinity. As I get closer to this line, closer to the sign.
Doesn't mean you go left to right anymore. It just goes whichever way.
Yeah, it doesn't mean left to right. It always means as I get closer to that line from the left, as I get closer to this line from the right. All right. We need to install these holes at -2. So here's -1, there's -2. So at this coordinate, we need to have a hole. So I'm going to install my hole right there. So I have a hole at -2. And I need to have a hole at +3. So I come over here to +3. There's 1, 2, 3 right here. I'm going to erase a little bit and install a hole. And there's our function.
Now I turn it in.
You don't turn in notes. No.
Oh, can I go back real quick?
Yeah.
I still